Hi. It's terrific to be here, and I'm really honoured to be invited to talk to the Australian Mathematical Sciences Institute. I speak at a lot of different organisations and contexts around the world in all sorts of different forums. But this is the first time I've actually formally been invited to speak to mathematicians. So I'm, by trade, I'm a science communicator. So it's a somewhat wondrous and somewhat daunting thing to be speaking to professional mathematicians. And occasionally I hope that they will chip in the conversation afterwards. So, my subject tonight is Corals, Carbon and the Cosmos, the story of hyperbolic space. And the subject here is mathematics. And I'm hoping to convince you today that mathematics is in itself an inherently creative subject. We live in a time when there's a lot of discussion about the need and the desire to engage people with mathematics and science. And one of the ways it's being talked about this is to integrate them with the arts. This is what some of you will know as the STEM, science, technology, engineering, mathematics, to STEAM movement, adding art into the equation. And STEM to STEAM is one of the things that I do in my life. I'm interested in combining the arts and the sciences in novel ways. One of the things I'm also interested in is the ways in which science and mathematics themselves have creative and poetic dimensions. And so I thought I'd begin by showing you this lovely quote by the mathematician John Playfair, who was actually formatively involved in the story of hyperbolic space, as we'll hear in a minute. So in the early 19th century, when all kinds of new mathematical objects, like hyperbolic geometry, were being discovered and coming into mathematicians' consciousness, Playfair made this wonderful statement: "We become aware how much further reason may sometimes go than imagination may dare to follow." And what he was getting at is that mathematics, through the mechanisms of logic and reason, can actually take us in truly enchanted directions. And that's what I hope to show you today. As Andrew said, what I do is I write about science, I design exhibitions about science, particularly at the intersection of science and art. And to this end, about 10 years ago, I founded an organisation where I live in Los Angeles, and the organisation is called the Institute for Figuring. And our mission is to engage people with mathematics and science by showing them the aesthetic and poetic dimensions of these fields. And for those of you who are mathematicians and computer scientists, some of you might already have noticed that our acronym is IFF, which is the logical symbol for if and only if. So if any of you visit Los Angeles, please come and see the organisation. Today we're going to talk about the branch of mathematics known as geometry, which, as many of you know, was formally articulated in 300 BC by Euclid. And here we see a picture by Raphael celebrating the discovery and invention of geometry by a mathematician who is assumed to be Euclid. I'm sorry, we are competing with the sunlight here, so I hope that you can see these images clearly enough. The geometry is a subject, formally, that goes back to the ancient Greeks, and it's inspired many, many people, apart from mathematicians, ever since. And one of the groups of people that it's inspired is the Renaissance artists, like Raphael, who painted this incredible painting. This is the whole of the painting that detail comes from, painted in the early 16th century. And what we see here is that this is what we call a perspectival image. And what this is trying to do is to represent on a picture plane a conception that the world around us has a particular kind of geometric structure, which is the structure of Euclidean space, And you all know what that means. To say that we're in Euclidean space is to say that we live in a three-dimensional void. Imagine a giant box with backwards, forwards, sideways, and up, down. This is a three-dimensional, as it were, vacuum that is imagined by the Renaissance painters to be the framework of reality. And geometricians had conceived of the conception of three-dimensional space a long time ago, but it wasn't until the Renaissance that people in Europe began to think that that was the framework of reality. And they begin to represent this in perspectival drawing from about the 14th century on, and culminating in the 16th century with the works of people like Raphael, Leonardo, and Michelangelo. Now, the idea that reality itself could be explained by geometry at all was actually very radical. We all learn geometry at school, and we're taught to think that the world around us is this Euclidean space. But actually, that idea didn't come into Western consciousness or anybody's consciousness at all until about the 13th century. And one of the first people to articulate the idea that we live in a geometric world was the Franciscan monk Roger Bacon, who in the 13th century wrote a wonderful book championing mathematics and science, and he articulated a notion of what he called geometric figuring. And what he meant by that was a new kind of picture making, a new kind of artistic representation that would be based on geometry, as opposed to the older forms of what we know as medieval imagery, in which there doesn't seem to be what we would call perspective, and things don't seem to be existing in early medieval imagery in a Euclidean homogeneous void. And Bacon was one of the first people we know of who said, this is the way the world is. And he termed this new kind of artistic representation geometric figuring. And that's the kind of imagery that 2 centuries later we see. This image on the left-hand side here is actually from the early 15th century by an artist named Paolo Uccello. And what we see here is what looks like a contemporary wireframe model. That looks like something from a piece of computer animation. But actually it's from the 15th century, and it's the earliest known image that we know of that is actually representing an object from multiple perspective points. In fact, it's believed that this imagery is actually representing this chalice from 17 different perspectival points. Now, we all recognize that as a mathematically geometrically inspired image. But what was one of the underlying issues that was inspiring people to do imagery like this was the view that Roger Bacon and others of his time articulated, that artists should represent imagery through the tools of geometry, as Paolo Uccello is doing here, because geometry is the way that God has designed the universe. So in the late medieval time, in Western Europe, an idea came about that God was a geometer, and God had designed the universe according to the rules of mathematics. So to represent it truly, that is the tools that artists should use. And that's what we see coming into being and reaching its apex with the artists of the late Renaissance, people like Raphael. We see these images where everything seems to be in a coherent mathematical space. It's a very, very radical thing. And it's wonderful to know that some of these artists were also not only the great artists of their time, but some of them were the foremost geometers and mathematicians of the time. So in the 16th century, mathematics and art were not considered separate things. They were seen as part and parcel of a practice that was combined about representing reality not only beautifully, but also truly. At the time, not only were artists painting pictures inflected by geometry, But architects were interested in building buildings and building cities inflected by geometry. And here are two representations from the 16th century of artists' renderings of what would be the ideal city. And the ideal here is meant to be Euclidean. It's beautiful lines, beautiful rectilinear. Everything is, as it were, with this kind of crisp geometric, specifically Euclidean perfection. And that is indeed how we have been building cities for hundreds of years. This is the top one is a picture of Rome, which, as you see, is very much inspired by these idealized representations. And the bottom one is, it's an American city, I think it's Chicago. But we, for the last probably 1,000 years, as builders, have been building ourselves Euclidean spaces. The rooms that we inhabit, the skyscrapers that we go to work in, the freeways that we cruise on, are for the most part parallel Euclidean rectilinear spaces. But it's interesting that outside of our architecture, outside of our visions, nature and other people have been playing with concepts that are not Euclidean. And today we have a huge desire on the part of artists to break free from Euclidean constructs, or what are seen as Euclidean constructs, and actually represent new, non-Euclidean forms. So I want to show you here a piece of animation that comes from the film Avatar, which is actually a beautiful representation not only of non-Euclidean geometry, but specifically of hyperbolic geometry. So where Renaissance artists saw the height of beauty as being a kind of Euclidean ideal, it's interesting that many artists of our time, particularly CGI-inflected artists working in video games industries and in films, are doing everything they can to present things that are swerving and swooping and not conforming to Euclidean principles. And it turns out that nature has also been playing with non-Euclidean forms for hundreds of millions of years. So here is an actual sea sponge. And it's exactly the same structure as those forms that you saw in the film Avatar. And this is something that you would find in the bottom of the sea. And it's a structure that's hundreds of millions of years old. Nature has actually been making hyperbolic forms since at least the Silurian age. And we see them in many different places. This is another kind of hyperbolic form that's a sea sponge. And corals, many corals are hyperbolic structures, non-Euclidean structures. And what we see here is that nature has, as it were, been doing geometry. And one of the things that I think is fascinating here is that while human beings spent hundreds of years trying to prove that anything apart from Euclidean geometry was impossible, critters like sea slugs have just been getting on with it. Which raises an interesting question of what does it mean to know geometry? One of the places where we all see non-Euclidean geometry represented is in lettuce leaves. Every time you eat a lettuce leaf, you're actually eating a hyperbolic surface. Cactuses, too, often make hyperbolic surfaces. All these swooping, curving, crenellated forms are hyperbolic structures. They don't conform to the principles of Euclidean geometry. Here's another cactus, a kind of swirling thing. And another one. This is interesting because these kinds of structures, which are also hyperbolic, actually result from a kind of plant version of cancer. And what it is a runaway growth that causes, as it were, hyperabundance of surface, which is one of the things that characterises hyperbolic geometry. So there's a very real sense in which hyperbolic geometry, with this kind of excessiveness, with this frilliness, and more than enough surface, as it were, is pathological. These cactuses are literally pathological. These are very, very beautiful forms. They're called crested cactuses. But as I said, it is actually a form of plant cancer. And that's interesting in part for the reason that when mathematicians first began to realise that there were hyperbolic structures, they too thought they were pathological. Mathematicians discovered hyperbolic structures, hyperbolic geometry, in the early 19th century, after spending literally 300 years trying to prove that anything like that was impossible. And at the time, it was believed that they were literally absurd, aberrant, deviant, because they didn't conform to the rules of Euclidean principles. And many mathematicians who were working on them in the early 19th century were literally driven, or almost driven mad, by these weird structures that they were beginning to realise existed. This is a statement by one of the mathematicians who was working on it, a man named Wolfgang Bolyai. For God's sake, he said to another mathematician, his son in fact, please give it up. Fear it no less than the sensual passions, because it too will take up your time and deprive you of your health, happiness, and peace of mind. Now, we don't usually think of mathematics as being something that could inspire that kind of emotion, either the happiness, the joy, or the madness of it. So what is it about hyperbolic surfaces and hyperbolic geometry that was, to mathematicians' minds, so pathological? If sea slugs and corals can be doing it, why is it so, as it were, abhorrent seeming to a mathematician? And the reason for that is that, as I said earlier, hyperbolic geometry broke with the principles that Euclid had laid down 2,000 years ago. And to many mathematicians, to break with Euclid was to break with the laws of logic, to break with the laws of reason. And anything that appeared to be contrary to Euclid therefore had to be wrong. Mathematicians wanted it to be wrong, but after 300 years of trying to prove that it must be wrong, they were forced to admit that actually this was mathematically correct and that there did indeed exist a kind of structure, a kind of geometry, a kind of space that wasn't Euclidean and didn't conform to Euclid's fundamental axioms. So let us just consider for a few moments what this structure is from a mathematician's point of view. And I'm going to show you that you all actually know a good deal more geometry than you think you do. You're all innately good mathematicians. It turns out that there are a number of different kinds of geometry, and Euclidean geometry is only one of them. The other two, that are the most common ones, are what's called spherical geometry, which you will find out in a moment, you all know a great deal about, and hyperbolic is another alternative. So let us consider how we can think about these different kinds of geometries. The classical way to do it is to think in terms of parallel lines. So in Euclidean space, we all know a simple question. If I take a straight line and a point outside my line, how many lines can I draw through the point that never meet the original line? And does someone want to tell me the answer? One. Yes, very good. You all know. And Euclid basically incorporated this into his fundamental axioms and said that it's only ever possible for there to be one line that goes through the point and never meets the original line. And that's what we call the parallel line. But mathematicians were a bit worried by this from the word go, because it seemed like a very complicated thing. It sounds like something that's, although intuitively it looks right when we see it, mathematicians, being very logical people, think, well, if that's absolutely necessarily true, we ought to be able to prove it in terms of a few simpler principles. It seems like a rather complex principle to start off with. And so they actually spent a long time trying to show that this must be true, that there could never be an alternative space where the answer was not 1. Now, you might think that all this is, you know, it seems so obvious, why do we need to prove it? But I can demonstrate to you that in something that you know of, there's another kind of space where the answer is not 1, and that's on the surface of a sphere. So let us ask the question, think about that as being a sphere, like the surface of a beach ball. And we can ask the question again. If we have a beach ball, and just imagine you're an ant walking around the edge of that beach ball, and you're confined to the surface of your beach ball, you can't go through the centre of it, so you're just confined to the surface. And we ask the question, what if we draw a straight line on the surface of our beach ball, and we put a point outside it? How many straight lines can I draw through the point that never meet the original line? Now we're immediately faced with a question. Now we're talking about a curved surface. What does it mean to talk about a straight line on a curved surface? Non-intuitive question. Again, mathematicians had to spend a very long time considering this. What does it mean? And they've come up with a generalised conception of straightness on curved surfaces, which is what is called a geodesic. That's the generalised term for straight. And what a geodesic is always the line that traces the shortest point between the shortest path between any 2 points. And on the surface of a sphere, the shortest path between any 2 points is always what's called a great circle, the biggest possible circle you can do. So if you think about the Earth, the surface of the Earth, the equator is a straight line. The lines of longitude are straight lines. And this turns out to be important in our lives, not just from a mathematical point of view, but there's a practical situation where we all encounter this. And does anyone want to suggest what that might be?
Flying.
Sorry?
Flying planes.
Yes, yes. So it is the case that when airlines chart out the paths they're going to take, say from New York to London, when you look at them on a map, they appear to be curved lines. So this is a map, in fact, of all international flight paths in the world. I hope it's not too... I hope you can see that, but you get the general idea that the lines on this map appear to be curved, but they are in fact straight when you think about them on the surface of the Earth. And the reason that they look curved there is because we are projecting from the surface of the Earth, which is a curved space, onto the flat space of a map. So all of those lines, actually, if you were on the surface of your beach ball, would be straight lines. And how do we know that? Because they're the shortest path. Now, they don't look the shortest path there, but I can assure you that they are the shortest path, because if they weren't, they would cost airlines a great deal of money. And the reason, does anyone want to guess what the reason for that is? Sorry?
Fuel consumption.
That's right, fuel consumption. So jet fuel is very, very expensive. If you're an airline that spends hundreds of millions of dollars a year on jet fuel, you want to use as little of it as possible. So with the help of mathematicians and cartographers, airlines have worked out how to take the shortest possible route. Now, given that I've given you a big hint, and think about what you know about the surface of the Earth, we can ask the question again. How many, if I want to be on the surface of a sphere, how many straight lines can I draw through a point that never meet the original straight line? Think about what you know about the surface of the Earth. And given that all of the straight lines are the biggest possible circles we can do. Yeah? Sorry? None. That is right. We can have, there's no such thing as a straight line on the surface of the Earth that doesn't intersect with any other straight line. If you think about the equator and the lines of longitude, they all intersect. So on the surface of a sphere, in the geometry of a sphere, the answer to our original question is 0. Now we have a geometric space where Euclid's postulate doesn't hold. Euclid said there must be one straight line that goes through a point that never meets the original line. Now we have a situation where there are none. So now we have two different situations. We have two answers to our question. In Euclidean space, the answer is 1. In spherical space, the answer is 0. To a mathematician, that says, well, why can't there be another answer? Could there be another answer? Possibly there could. And it turns out that there is. There exists a mathematical space where I can have a line and a point outside it, and it turns out that there are an infinite number of straight lines that can pass through the point and never meet the original line. And this is what we call hyperbolic space. And it's called hyperbolic because it seems like there's an excess of everything. Now, you're all sitting there looking at this diagram and saying, I'm cheating, because those lines look curved. But just as we had to distort the map of the Earth when I showed you the map of the flight paths, because we're trying to project an image of a curved surface onto a flat map, that's why this image also looks like the lines are curved, because I'm projecting a curved, I'm trying to project an image of a curved space onto a flat wall. But I can prove to you that these lines are are straight, if you were thinking in terms of being on that surface. And that's because I can demonstrate it to you physically, because here we have a model of hyperbolic space, hyperbolic geometry, and it's made out of crochet. And we'll talk about that in a minute, why we're crocheting. But this is a model of a hyperbolic surface. It looks like one of those cactuses or corals that we saw earlier. And here we have represented on it Euclid's postulate, that here is a straight line, here is a point outside the line, and there are 3 different lines going through the point that never intersect with the original line. And again, you're probably saying, well, you know, they look pretty curved to me, but I can prove to you that they are in fact straight. And that's because if I take any one of these lines, I can fold along it and make it a straight line. And from the point of view of a mathematician, that is a tangible demonstration that it is straight. So here in crochet, we can demonstrate the most famous proposition in mathematics was wrong. And this is done with a ball of yarn and thread and a crochet hook. And it turns out that one can demonstrate a whole lot of mathematical principles by literally stitching them onto the surface of these hyperbolic models made out of crochet. And although this doesn't introduce any new mathematics to a mathematician, what these crochet models do is provide us with a tangible physical way to see the abstract principles embedded in hyperbolic geometry. So one thing that you can demonstrate onto a model like this, for instance, is that not only do parallel lines behave differently in hyperbolic geometry, but so do things like triangles. So if I was to stitch a triangle onto the surface of this hyperbolic surface, what we would see is that the angles of a triangle don't add up to 180 degrees, they add up to less than 180 degrees. And in fact, you can even have an extreme case where the interior angles of a triangle add up to 0 degrees. Now, when I was a university student doing mathematics, we all had to kind of take that on faith. We learned it through textbooks and equations. It was very hard to kind of comprehend. But in 1997, Dr. Dana Tamina, a mathematician at Cornell, figured out that she could make physical models of hyperbolic geometry using crochet. And a lot of mathematicians up until that time had believed that you couldn't have models of hyperbolic geometry. But Dr. Tamina came along and said, well, you know what, boys, I can crochet it. Actually, you can knit them too, and the first one she made was knitted, but it's easier to do it with crochet. So Dr. Tamina, with this feminine handicraft, gave us a way to make physical models of a kind of mathematics that some of the greatest mathematicians of our culture had thought was impossible. And it may seem like an interesting question. How come sea slugs and corals had been doing this for hundreds of millions of years and humans hadn't been able to make models of it? And that's a really interesting question. It's actually a very difficult thing to model hyperbolic surfaces. Why did human beings not only not be able to model it, but think that they were impossible? And I once asked some mathematicians, why, given that hyperbolic geometry was embedded all around us in things like sea slugs and corals and cactuses, why had mathematicians not recognised that? And it turns out to be a non-trivial question. A flippant answer to it was, well, perhaps there weren't that many mathematicians sitting around studying sea slugs. And that's probably true, and there probably still aren't. But at least some mathematicians that we know of have in fact eaten lettuce for lunch. In fact, there's this famous story about the mathematician Kepler eating lettuce for his lunch. So why didn't mathematicians recognise that hyperbolic geometry was actually this very ancient thing all around them, literally in the flowers in their garden, in the lettuce in their salads? And it turned out to be that these structures did not conform to their ideas of what mathematics could be and what it could do. And when hyperbolic geometry was discovered, it helped to usher in a revolution in our geometrical thinking and ultimately helped to precipitate a revolution in mathematics itself. So these lovely surfaces, which you can make with crochet, turn out to be something that is embodying principles that lie now at the foundations of a whole new field of what's called non-Euclidean geometry. So hyperbolic geometry, of which these crochet models are all instances of, are a subset of a much broader field of mathematics, which is now the geometry of the generalised field of what's called non-Euclidean geometry, which allows us to describe any curved surface. And that's the kind of geometry that people who are doing CGI worlds, making virtual reality worlds in computers, or for films like Avatar, they have to, underpinning the beautiful representations that we see on the screen and love in films like Shrek or Toy Story, is this understanding of how to model variously curved, infinitely variable surfaces. One of the questions that this new field of non-Euclidean geometry raised was if there are different mathematical possibilities for the structure that a space can have, if it could be flat or spherical or hyperbolic, what is the shape of the space of our universe? And from the early 19th century, from the time when mathematicians began to explore hyperbolic structures, it came into their consciousness, is the space of the universe around us Euclidean, or is it something else? So as I said earlier, perspective painters, Renaissance painters, took it for granted as an ipso facto point of logic that the space of the universe must be Euclidean. And people like Kant tried to prove that it was, or Kant actually just took it for granted that it was. He proposed that Euclideanness was a fundamental quality of being. And Newton took it for granted too. But with the coming into being of general relativity with Einstein in the early 20th century, there came to an understanding that in fact the space of our universe may not be Euclidean at all. It could be Euclidean, but it could also be spherical, and it may be hyperbolic. And at the moment it's an open question. It's one of the great questions that astronomers are trying to answer by sending these great telescopes like the Hubble Space Telescope out there into the void. One of the big questions we're trying to understand is what is the structure of the universe as a whole? And although most of the evidence is that the universe at large is a Euclidean, it turns out that there is some evidence that we might just live in a hyperbolic world. If the universe is hyperbolic, it's not a simple hyperbolic structure like the shape of a lettuce leaf. It's a rather complex hyperbolic structure that's folded back on itself. But isn't it wonderful to know that through this arcane mathematics, which was once upon a time just seen to be a completely abstruse area of mathematics, that this is ultimately going to tell us about the shape of the universe as a whole. Now, according to general relativity, the universe has a structure which may or may not be hyperbolic, may or may not be Euclidean, but that structure is four-dimensional. We have 3 dimensions of space and 1 dimension of time. So with relativity, we have to imagine that the universe is not just a 2-dimensional surface like the surface of our beach board. It's an analogue of that, but with 4 dimensions. And the reason that I mention that is because here we have 2 calla lilies, which are the kind of flowers you might buy, have on your table one night for dinner. And these are hyperbolic structures. And it turns out that there's a group of physicists at the University of Austin, Texas, who have been modelling how flowers, like calla lilies, make these beautiful swirling hyperbolic structures. And in order to make the mathematical models, they actually have to do the modelling in 4 dimensions. And so it also raises the question here, if we humans have to make our models of a flower in 4 dimensions in order to, as it were, correctly represent what the flower is doing, does the flower itself somehow know 4 dimensions? Is the flower aware of 4 dimensions? And what does it in fact mean that these simple brainless organisms are literally embodying in the fibres of their being mathematical structures that the greatest mathematicians on Earth need supercomputers and multiple dimensions to make? I said earlier that there are different ways of understanding hyperbolic geometry. One is in terms of parallel lines, but another way of doing it is in terms of how you can fill the surface with shapes, like tiling your bathroom floor. And you can think of this, literally it's like tiling, the mathematical term is tessellation. But we can characterise the different spaces that these 3 different geometric structures by the tiling patterns you can make with them. So on a Euclidean space, we can fill the space with hexagons. If we want to make a model of spherical space, we have to replace some of the 6-sided ones with 5-sided ones, and by literally taking some of the sides out, we pull it in and make what's called a positive curvature space. Now, if that's the way we make a model of spherical space, what do you think we do if we want to make a model of hyperbolic space? What specifically would we do? Someone said we open it out, which is the right answer, but there's a specific thing. So here we replace some of the 6-sided ones with a five-sided one. And we pulled it in. So what would we do if we wanted to open it out?
Four-sided one?
Four-sided. Think in the other direction. What we do is we actually replace it with seven-sided ones. And by literally adding more sides, we add space. And again, get this kind of excessive arrangement, this kind of excessive fluting. And you can actually make models of these things out of paper. So this is a model of that six-sided and seven-sided structure made out of paper. And it's very interesting when you make these, because the paper really doesn't, paper which is intrinsically a Euclidean thing, really doesn't want to go into these fluty structures. And when you force it, you sticky tape them together, and you have to do a lot of sticky taping to, as it were, overcome the Euclidean, as it were, tendencies of the material itself. So one of the things that's really beautiful is that these three spaces, Euclidean, spherical, and hyperbolic, these are models. But it turns out that there's something in nature that actually emulates these models. And what it is carbon atoms. So you can take carbon atoms and make them form all these three different structures. And all of them have turned out to be structures that are the foundations of fundamental new fields of material science. So the Euclidean example, where we have flat sheets of carbon atoms, is what's called graphene. And it can be laid out in big flat sheets, or it can be wrapped into tubes, which are called carbon nanotubes. And the year before last, the Nobel Prize in Physics was given to the people who discovered graphene. And it's turning out to be a revolutionary new material that is allowing us to do all sorts of things like produce superconducting wires. Nanotubes are at the heart of many different new technologies and materials, everything from sunblock to new forms of electrical conductors, and may be the foundation of a new kind of revolutionary electronics. About 15 years ago, it was also discovered that carbon could be arranged into the structure of soccer balls, like on the left, and that there was a whole, they're called buckyballs, after the great architect Buckminster Fuller, because they have the same structure as geodesic domes. And there's a whole series of these chemical compounds which are now, as it were, generically called fullerenes, or Buckminster fullerenes. And they too are turning out to have amazing material properties that are going to produce all kinds of new revolutionary, make possible all kinds of new revolutionary technologies. And even the hyperbolic version can be realized in carbon. So carbon atoms can be made to arrange themselves into hyperbolic structures. And that was a discovery made here at the ANU in 1997. Nobody has yet found a use for these, but it is just a marvellous thing that carbon, a simple brainless atom, can be made to realise the three fundamental geometric structures that mathematicians themselves struggled with. I will just end by saying one can also play with hyperbolics in a purely artistic sense. For the last 10 years, I've been spearheading a project where we've been using hyperbolic crochet to make models of coral reefs. Because the reason that corals look like hyperbolics is because corals themselves are actually performing hyperbolic structures. And with crochet, you can make beautiful models of corals and put them together in landscapes and build up what looks like huge coral landscapes. And it turns out there is a whole taxonomy of hyperbolic crochet coral species, just as there's a huge taxonomy in nature of hyperbolic reef organisms. So you can model these with feminine handicrafts such as crochet, beading, knitting, and tatting. And for the last 10 years, my sister and I have been spearheading an international project where we work with people all over the world to build huge coral landscapes. It's a project that's at the intersection of mathematics, art, science, craft, and environmentalism. We've done it with 8,000 people in 12 countries in 35 cities. And every one of those exhibitions, and we've had exhibitions in galleries and science museums all over the world, most of them in art galleries. 2 million people have visited these exhibitions, and all of them, through the exhibitions, have been exposed to mathematics. Whenever we do the exhibitions, we devote a portion of it to basically explaining these three geometrical structures. So one of the ways in which people can be engaged with mathematics, I believe, is not just through learning it as if it's a chore, which is what unfortunately too many people think of maths as being, but learning it as a way to make something beautiful, to make something artistic, and to literally have the opportunity to play with the geometric forms. So who would have thought that through a piece of mathematics one could find links between crochet corals and the cosmos? We're used to thinking in our society that mathematicians are over here, crafters are over here, biologists are over here, material scientists are over here. But through the mathematics of hyperbolic space, all of these things intersect and weave together. And I think it's a lovely story about how mathematics is everywhere in our lives. It's not just something for a few boffins to be doing over at the blackboards. It's for everybody. Mathematics is all around us. Geometry is everywhere. It's in the sea, it's in the air, it's in atoms and stars. Mathematics is something that underlies everything in the world around us. And I hope that this has enabled you to see that mathematics is also in itself a beautiful, creative and poetic field. So thank you very much.
My name is Jeff Prince. I'm the Director of the Australian Mathematical Sciences Institute. And so we're going to take some questions from Margaret. Before I do that though, I just want to thank Margaret for an inspiring lecture on one of the boffins. I'm not sure, so there are many of you here who aren't mathematicians, but from a mathematician's perspective, I think it's wonderful to hear some of the artistic and social connections and aspects of mathematics that most of us either don't know, working mathematicians like me don't know, or on a day-to-day basis we don't think about it. And it's absolutely enlightening to hear such a wonderful talk. So before I hand over to Margaret to manage the questions, I just want to say a couple of things about AMSI. AMSI is the National Mathematical Sciences Institute. We put on a number of programs across the entire mathematical sciences pipeline, from primary schools right the way through to research training and researching companies and universities and university teaching and so on. Our membership ranges across the entire country. Almost every university is a member, along with the learned societies and various government agencies. It's an absolute privilege to be the director of AMSI and to come along to public lectures like this, but also to be able to run the summer school, which is on at the moment. So this is a 4-week residential school, which we're very pleased that RMIT is hosting this year, and Margaret's lecture is part of that school. So I just want to thank a couple of sponsors. CSIRO, the Department of Education and Training, is a sponsor of many of AMSI's higher education programs. The Australian Maths Society, Optiva and City West Water are all sponsors of the summer school and the lecture. So thanks very much to all of those. So Margaret now, having said all of that, Margaret will take some questions, and at around, well, in a little while anyway, we'll call an end to the formal questions, and those of you who have to go will be able to go, and those of you who wish to go on and talk to Margaret will be able to do so. So please, Margaret. So can we put your hand up if you'd like to ask Margaret a question?
Or make a comment? Yeah.
Can we go with this one first?
No.
Oh, sorry, there's a screen in front of me.
Thank you, Margaret. Margaret, do you think that women mathematicians bring a different perspective to mathematics?
I don't know if that's the case. I think it's very hard to say whether that would be true or not. One of the things that I think we should reflect on is that women now being able to do mathematics at all levels are achieving math at extremely high levels. So last year, for the first time, a woman mathematician was awarded the Field Prize, the Field Medal, which is the mathematical world's equivalent of the Nobel Prize, and an Iranian mathematician, Mariam Mirzakhani, was awarded the Field Prize last year, which I think was absolutely wonderful because it proves that women can do math at the highest levels.
Thank you very much for the for a very interesting lecture. Comparing art, architecture, and mathematics, could one say Bauhaus and Cubism belong to Euclidean geometry, whereas Baroque belongs to hyperbolic geometry?
Who belongs to hyperbolic geometry?
Baroque art.
Oh, Baroque art, right. I mean, it's interesting because there was in the late 19th and early 20th century, there was a whole movement of artists who were inspired by thinking about geometry, and specifically by trying to think about geometric forms in 4 rather than 3 dimensions. But they weren't specifically thinking about hyperbolic space. The artist who is specifically inspired by hyperbolic geometry was Escher, M.C. Escher. So this is one of Escher's most famous series of works. It's called the Circle Limit series, and they are actually very specifically representations of hyperbolic geometry based on this model, which is called the Poincaré model of hyperbolic geometry. And that is a representation of hyperbolic geometry projected onto a flat plane. And Escher took it up and made it his mission to learn hyperbolic geometry very seriously, and produced this famous series of works. And it's now known that, in fact, Escher made a discovery through his painting or his drawings about hyperbolic space that was fairly recently verified by computer simulations. So if one wants to look at mathematicians who've been inspired by, artists who've been inspired by hyperbolic space, the famous one is Escher. But there have been certainly other artists who've been inspired by non-Euclidean geometry, and a famous one, of course, an architect, of course, is Gaudi, who made these beautiful curving, dripping looking buildings, and he was very specifically trying to model non-Euclidean geometry also.
Thanks. I'm interested in the structure of plants.
Sorry?
I'm interested in the structure of plants, and when you were speaking about the way that mathematicians are looking at them, you said that they were using the fourth dimension.
Mm-hmm.
I just wondered what you meant by that.
Well, what is going on with that is that physicists who are trying to model how plants make those swirling curvy forms find that when they make their models, where do we get to? That if you want to model the formation of these swirly geometric structures, in order to get the models to work properly, they have to make their models with a four-dimensional representation of it. So what does that mean? You know how when you see animation in film, it's what you're seeing is like when we saw the Avatar film, you're seeing the form, you're seeing the picture on a two-dimensional surface. But when they model, they build computer models. Or let me show you something that might help with this. You're asking a very difficult question. Essentially, you're asking a question: what does it mean to say something is four-dimensional? So, when computer modelers when computer animators make models of things, they build a model that in the computer model it is represented with 3 dimensions. So you can see that these are like 3-dimensional. You can imagine that as a wireframe model with having 3 dimensions. And so when computer animators make pictures, underlying the 2-dimensional pictures are encodings of a 3-dimensional structure. But in order to represent how the flowers do what they do, you actually have to model it in 4 dimensions.
Because you have to see it expand.
So it's a 4th physical dimension. There's a 4th dimension of physical dimension.
Well, so this raises the huge question of what does a dimension mean? Which we could give a whole talk on that subject. So for a mathematician, a dimension is just represented by a set of points. So a simple way to think of this is, if I want to represent any point on a plane, I can just have an x and a y. So I have an x-axis and a y-axis. And I say it's there, which means it's 3 units along the x-axis and 4 units up the y-axis. If I want to represent a point in this room, I have to have 3 axes, x, y, and then a z dimension. It turns out that if you want to do an accurate representation of what the flowers are doing, you need another dimension. It's not because the flower is growing, it's because underlying that structure is somehow a 4th dimension encoded into it. Now, for a mathematician, a dimension doesn't have to have a physical analogue. We're used to thinking of dimensions. Most people who think, most of us are used to thinking about dimensions as being physical things. But to mathematicians, dimensions are just, as it were, a code. And I can represent from a mathematician's point of view, I can posit a structure in 17-dimensional space or 80-dimensional space or 1,000-dimensional space. And from a mathematician's point of view, the dimensions all have just as much reality, because it's just in some sense a code. But the code's useful in that it can be descriptive of things that you can't, say, describe with a 3-dimensional code. So there's no simple answer to the question that you're asking. But it...
Thank you, Margaret. I was just thinking as you were describing the mathematicians in the past and possibly even now, failing to recognise certain aspects of certain examples of hyperbolic space in nature. But I was thinking of it in a different way, and that was that somehow in the past, especially before the 20th century, a lot of mathematics was thought of in a way that simplified, that either by extending a concept infinitely or by contracting it down to zero. In other words, looking at something globally, looking at it locally, and therefore you could take hyperbolic space as an example of that and say, well, you know, a real hyperbolic space is something that is necessarily infinite in extent. And it's only now in the 20th century, especially with computers, that we can start looking at things that are finite but arbitrarily complicated. And so we can start thinking about things like, well, what does a patch or a disk of hyperbolic space look like? And then exactly the examples that you've shown are these disks which are finite in extent but can be arbitrarily complicated. Can you comment on
that? I'm not quite sure what the question is, but let me... there's a lot of issues going on. One thing that you're raising, which I think is a very interesting issue about mathematics, is you're saying that in some sense mathematicians have expanded from simple concepts out to more complex concepts. And that's really true. Mathematics, the history of mathematics can be seen in one way as the history of expanding imaginations. And mathematicians have gradually realised that very, very simple things can actually contain very complex possibilities. So here's a really simple thing. In the beginning of our thinking about numbers, we just had very simple numbers, 1, 2, 3, 4, which we used to count with. You know, 1 sheep, 2 sheep, 3 sheep, 4 sheep. Then somebody came along and said, what about the idea of 0? And some cultures, like the Indians, accepted 0 as a number. And some cultures, like the Western world, for a long time said, no, we're not going to accept 0. Because you can't, they literally said you can't signify nothing. And then there was an idea, well, what about a negative number? What about -3, -4, -1, 2, 3, 4? And initially mathematicians in the Western world said, no, can't have that. Doesn't make sense to talk about a negative number. But in the 13th century, negative numbers became accepted, and there was a very simple reason for that. You can't have -4 sheep, but you can have -4 something. Does anyone want to guess what the -4 you can have? Sorry? Dollars! You can certainly have -$4. It's called debt. And the reason that the negative numbers got accepted into mathematics was because it coincided with the coming into being of double entry bookkeeping. Bookkeepers, accountants knew exactly what a negative number meant. You owe me money. And that was actually how negative numbers got incorporated. So now we've gone from, the concept that numbers are counter, just positive things in front of you, to that now there's a zero, this mysterious no number, and then there are these negative things. And then it turns out there are all kinds of other numbers, like what's called the imaginary numbers, which they're called imaginary for it's kind of an arbitrary reason, but it's this other literally it's another dimension of numbers. And they were originally invented for a very abstruse mathematical reason. But now it turns out that we know that you need these imaginary numbers to describe electrical systems. So, whenever you turn a light dimmer up or down, in order to describe that, physicists use a set of equations that incorporate these imaginary numbers. And there are all kinds of other numbers now that mathematicians know about that at first were usually invented for abstruse reasons, but gradually have come to be seen as actually modelling real-world things. But here's a question. If I, as a mathematician, come up with some abstruse system and some new form of numbers that don't appear to have any embodiment in the real world, does that matter? And one of the things that happened soon after the discovery of hyperbolic geometry and a few other seemingly absurd mathematical things around that time was that mathematicians realised in the mid-19th century that mathematics doesn't have to be about anything. It doesn't have to be about anything physical or real. And they came to the realisation that mathematics doesn't have to be about anything other than itself. And that's really the revolution that hyperbolic geometry helped precipitate. That in a sense, mathematics is a realm of pure imagination. If I can think of it and it's logically consistent, then it's a legitimate mathematical construct. And so you're right that mathematics is, as it were, about a gradual complexification of simple things. And in a way, it's about just letting go, letting your imagination free. Do you have to be bound by anything at all? And if mathematics is anything, it's the articulation of pure imagination. So I think we should probably wrap up there because it's past. So thank you very much to AMSI for inviting me, and thank you all for coming.